Okay, back to the start. So welcome Monday, December 7th, our class session. These are the topics we're talking about this week. Today, we'll talk about these first two. Complex numbers in trigonometric form, but specifically today, powers and roots. Then we'll talk about polar coordinates so that we can finish up on Wednesday with polar graphs. And I just want to go back to my website once again to make sure you're clear on the last homework assignment. So week 15, well, let's start from the top. These are the last three things we're going to discuss this week, and next week is just review and exam. So roots of a complex number, polar coordinates, equations of polar coordinates, polar graphs. Inside week 15, your last written homework is due tomorrow. That's the last written homework. You have no written homework for next week as you're preparing. But these three sections we're talking about this week, you are going to do the XYZ homework on those. Due Tuesday night, December 15. So you're going to have those done by Tuesday, 11:59. And then Tuesday, just before 11:59, I will release the exam. And so we'll have a review session on Monday where I'll answer any questions you like. I'll release the exam late Tuesday night, and you have until Thursday to complete the exam. So when you come to class on Wednesday, you can ask questions. They might be related to the exam, but I won't answer exam questions. But that's all we're going to do here in week 16. I'll release the exam Tuesday night, review Monday, release exam Tuesday, answer any final questions you have on Wednesday, and then you submit those by Thursday, 11:59. So pretty much the same procedure as first exam. I'm still writing the second exam. As I said before, I think it's going to look similar in length to the first exam. The questions, of course, are from chapters 5, 6, 7, and 8, not 1, 2, 3, and 4. So, there might be 5 to 6 questions in there. Maybe I'm not looking at 6. I haven't made up my mind. But the questions will be of a similar quality to your written homework problems, the other problems you've been doing. Now that you saw our first exam, you have a feeling for how I would ask you questions. Okay, that's just a summary. So if you have any other questions as they occur to you, don't hesitate to shout them out. And you could ask more questions. Wednesday, and you can ask more questions next Monday. So distributed Tuesday, December 15th, due 48 hours later. Which is Thursday, December 17th. Okay. Let's see what we can get going here. Let me reset that. Good. I've got that pinned in the right place. Good. Okay. Let's finish up the excellent properties of the trigonometric form of complex numbers. And that is, in particular, how I can use the trigonometric form to do powers and roots. So let's take this number 1 plus 2i. Let's call that z1. Let's take another complex number, Okay, what do I want to say? 1 minus root 3. I'll say 2 minus root 3i. And even if this got a funny root 3 right here, you know that it's very easy to add these. I just get 3 for the real part and 2 minus root 3 for the imaginary part. I just add like terms. I can't combine 2 and minus root 3, but that's okay. I'll just write them together with the parentheses. I got some screen lag here, but we'll deal with it as best we can. I can subtract them just as easily. Sure, I can multiply them, but the multiplication, foiling things out takes a little bit of work. So I get 2, and I get minus root 3i, and I get plus 4i, and then I get plus 2i minus root 3i multiplied. So plus times minus is minus 2 root 3i squared, but the I squared is negative 1. So this is plus 2 root 3. Then those pieces belong together, and those pieces belong together. So when I put those pieces together, I get a funny thing in the real slot here. 2 plus 2 root 3 plus, I get a funny thing in the imaginary slot too. 4 minus root 3. But there was another way to write these called trigonometric form, where I just multiply by multiplying the radiuses and adding the angles. So do a little bit of review here. If you have two complex numbers described in trigonometric form, the multiplication is a little easier to write. Division is a little easier to write. Z1 times Z2 will just be R1 times R2 cosine theta 1 plus theta 2 and I sine theta 1 plus theta 2. And the division of Z1 and Z2 just be R1 divided by R2 times cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. That's a lot better than foiling things out. Remember also, we showed you another abbreviation last week. Instead of, this is a lot of writing, R1 cos theta 1 plus I sine theta 1. A lot of people just write this as R1 cis theta 1, which stands for cosine plus I sine of theta 1. And they would refer to that as R2 cis theta 2. And then the benefit here is you can write R1, R2 cis theta 1 plus theta 2. That's a little too crowded there, sorry. And R1 divided by R2 cis theta 1 minus theta 2. So don't be afraid to use the shorthand for cosine plus I sine, cosine theta 1 plus I sine theta 1. But that was what we did last time. And to remind you how you find the R and theta, you have to draw these complex numbers in the complex plane. For example, Z2 is 2 on the real axis and minus root 3, about 1.7, on the imaginary axis. So this number right here is 2 minus root 3i. Now you could figure out this angle by saying here's a 2, here's a root 3, here's a triangle. What's the inverse tangent of root 3 over 2? And then you can name that angle right there. Likewise, this is Z2. I did it backwards. Z1 would be 1 plus 2i. Would look at a triangle like this. 1, 2, radius root 5. And then you have to work out what this angle is. Here the radius, 2 and root 3 would be 4 plus 3 would be root 7. Okay, so that's just very quickly drawing what we did last time. Let's do another example and draw it more carefully. But what instead if I wanted to multiply? What would happen if instead of multiplying, I wanted to do repeated multiplying? Oh, sorry, got to get someone else in the room here. What would happen if I wanted to calculate powers of some complex number? So let me do a complex number here and yeah, let's take Z2, which is 2 minus root 3. I. Let's draw this more carefully and examine the angle. Something doesn't feel right here. No, I want to change this number. So let me think about this just carefully here for a second. I'm trying to make sure I make up an example that's not going to be like impossible for us to calculate. So let's try a different number entirely. How about Z3, or just Z for that matter, is root 3 minus 1i. Okay, where is that? Root 3, let's say this is 2, is about 1.7-ish. Down 1, be down here, like that. There's a point Z3. This angle doesn't really catch your attention until you fill in the triangle. If this is root 3 and this is 1 downwards, you could also just write root 3 minus I. Then this is what? Short leg, long leg of a 30, 60, 90 triangle. What's the hypotenuse? 1 plus 3, 1 squared plus root 3 squared is 1 plus 3, which is 4. Square root of 4 is 2. This is a 30, 60, 90 triangle. Short leg, half of long, hypotenuse. This is minus 30 degrees right here. Or 330 degrees. You know, your choice. You could use either one. Stick to the positive angle for a second. So this standard form complex number can be written in trigonometric form as 2 times the cosine of 330 plus I times the sine of 330. And we mentioned this last time to prep you, but now we're going to actually do the calculation. What happens if we wanted to square this? That we'd multiply this by itself. I don't need to rewrite this to see it multiplied by itself, but maybe it'd help you see it a little faster. How do I multiply this thing by itself? Well, I multiply 2 by 2 and get 4. 2 squared is 4. And I take cosine of 330 plus 330. I'd add the two angles and multiply the two radiuses. And literally take r squared and do the cosine of 2 times theta 3 plus I sine 2 times theta 3. Let's let theta 3 be the angle, 330 or minus 30. Just stick with the z3. That's what happens if I want to square z3. If I want to raise z3 to the 5th power, what would I do? Raise r3 to the 5th power and take the cosine of 5 times theta 3 plus I times the sine of 5 times theta 3. Now, automatically, you see this is much easier. I haven't done the calculations yet, but imagine what would happen if you had to do z3 squared by foiling. You multiply this by itself. That takes a little work. But what if you had to raise z3 to the 5th power by foiling? Then you'd have to multiply this by itself 5 times. I'm almost reluctant to write that. Kind of reluctant to write that, first because it's too much writing, and second because I would never, no one would ever ask you to do it this way. That'd be a horrible amount of multiplying. But here I just have to raise the radius to a power and multiply the angle by that number, 5 or 2. So let's do z cubed squared. Radius is 2, so 2 squared is 4. And the cosine of 330 plus 330, 2 times 330. Now 2 times 330 is 660. Subtract a 360, you'd say that's cosine of 300 plus I sine 300. I'm going to pull in the calculator in a second to show you that this is correct. If you wanted to use the minus 30 and double the minus 30, you'd also be okay. You would write your answer as 4 cosine minus 60 degrees plus I sine minus 60 degrees. Both of these multiply by 4. In the abbreviated notation, this is 4 cis 300 and this is 4 cis minus 60. Now I can actually figure out what these numbers are because 300 and minus 60 are both nice numbers. But I could still compare it and calculate the answer even if they weren't nice numbers. 300 is 60 degrees shy of a full circle. This is a 60-degree angle right here. Minus 60 or 300 if you want to say it that way. Radius is 4. And remember, short side is half radius. half the hypotenuse, and long side is 2 root 3 times short side. So this point right here, z cubed squared is 2 minus 2 root 3 I. The minus because I went down on the imaginary axis. Oh, sorry, my paper was not advanced. Real axis, imaginary axis. Let's run that in the calculator and see if I get 2 minus 2 root 3. Let's have the calculator square this. The calculator doesn't mind so much squaring this. Before we do that, let's also prepare to check the fifth power. What's going to be the fifth power of z cubed? Well, z is made out of 2 cosine 330 sine 330. I'm going to say 2 to the fifth. Cis 5 times 330. The 5 times 330 is a pain. I think in that case, I might rather want to say 5 times minus 60, which is negative 300. Of course, negative 300 degrees is a positive 60 degrees. So that's 2 to the fifth, cis 60. You got to be happy with coterminal angles. That's 32 times cosine 60 plus I sine 60. And the cosine of 60 is 1/2. And the sine of 60 is root 3 over 2. So if we're telling the truth about z cubed, or about z3 squared and z3 to the fifth, I can check it instantly on the calculator. Okay, my fault. I'm not advancing this paper nicely. Let me number the papers so we keep track of them. Okay. Let's go check this out on the calculator. Since that was getting crowded, let me rewrite it here before we go. Root 3 minus I claim that z squared, z squared is 2 minus 2 root 3I, and z to the fifth is 16 plus 16 root 3I. Let's pull that up in the calculator here. And I got my camera backwards. If I write that way, then I can have the camera better situated over here. Let's get the calculator closer to the camera. Okay. So what is square root of 3 minus I raised to the 2 power? Well, the calculator gives me a funny number right there. Not 2 minus 2 root 3I, because the calculator doesn't do anything but approximate. But I can type in 2 times the square root of 3 minus 2 times the square root of 3. And I can see that it's the same number. So the calculator confirmed that this is 2 minus 2 root 3I. What about z to the fifth? Maybe you could imagine yourself squaring that number. But I don't think anybody would choose to raise that number to the fifth power with their bare hands. Raise it to the fifth power. Did I do that oddly? Cosine of 60, something doesn't look right. Now, what I got is some strange idea like, okay, you are got a 16 in there. I bet 16 root 3 is 27.7. But we must have made a mistake otherwise because I got the numbers reversed. Okay, 16 root 3 is 27.7. So why is this incorrect? Let's go back here and make sure I multiplied my 60 correctly. Oh, okay, here's the situation. I was using 60 from 2 times minus 30. So this number right here should be minus 30. The angle up here was originally minus 30. Sorry about that. So z to the 5th, which is root 3 minus I to the 5th, which is 2 cis minus 30 to the 5th is 2 to the 5th cis minus 150, and minus 150 is over here, 30 degrees shy of minus 180. So this is 32. This is 16. It's going to be negative in the I direction, and this is 16 root 3. So the proper fifth power here is 16 root 3 minus 16i. That's the correct answer. Let's scribble out that portion there. Okay, that's what I got for here. This is 16 root 3 minus negative 16 root 3 minus 16i. Let me wipe the ink off my screen. Okay. So trigonometric form excels at making powers. How about the opposite of making powers? The trigonometric form of a complex number is excellent. Sorry, center of the paper. For multiplying and dividing but now I also know it's excellent for taking powers. The fancy word for that is exponentiating. When you exponentiate something, you raise it to a power. But remember, roots are also powers too. So you can also take the square root or the cube root of the 5th root or the 10th root of a complex number easy in trigonometric form. So if you have a complex number, r cis theta, and remember, I'm using that as an abbreviation for r cosine theta, I sine theta, r times both those pieces. Then if I want to raise it to a power, I just raise the radius to that power and multiply the angle by that power. But that also works for roots because in the algebra class, you would have learned that the square root of a number is just the 1/2 power of that number. The cube root of a number is just the 1/3 power of that number. Any root you take, you can represent as a power. Nth root is the 1/n power of a number. So if you use the format for raising things to a power, then the nth root of a complex number is the nth root of the radius times the cosine plus I sine of the theta divided by n. But remember, you could consider that there are many numbers you could square to get another number. For example, when you want to square a number and get 4, you could square 2 or minus 2. Right? If you want to raise something to the 4th and get 16, positive 16, you could raise minus 2 or 2 to the 4th. This is just the principal square root, or the principal nth root. And the full answer in complex numbers is much more beautiful than just one root. Let me draw you another picture. Let me say it like this. If I was talking only about the real numbers, and if I asked you to solve this equation from your algebra class, you would come back with 2 answers. Let's draw those 2 answers. Even though they're just real numbers, let's draw them in the complex plane. Here's a 4. And the 2 answers I got were 2 and minus 2. Let's think of those 2 answers as complex numbers. Even though they're on the real number line, they do have angles. This number right here has a radius of 2 and an angle of 0. This number right here has a radius of 2 and an angle of 180. Now, you and I both know that when you square 2, you get 4. When you square minus 2, you get 4. But does that work in the complex description? Let's square 2 times the cosine of 0 degrees plus I times the sine of 0 degrees. How do we raise that to the second power? We square the radius and we multiply the angle by 2. Of course, 2 times 0 degrees is just 0 degrees. And 4 cis theta, where the theta is 0, is just this real number 4. How about squaring this number? 2 times the cosine theta plus I sine theta of 180 degrees. What happens when I square that? Same thing as before. I square the 2 and I multiply 180 by 2. Cosine 2 times 180 plus sine times 2 times 180 I. And that's 4, and 2 times 180 is 360. But the cosine of 360 plus I sine 360 is the same as cosine of 0 plus I sine 0. 0 and 360 are coterminal. So this is also 4. So the square roots of 4, the two roots square roots of 4 were cut into two pieces separated by 180 degrees. Let's try another one. So I just wanted you to see these numbers in the complex plane. Let's try something else simple. What if I asked you to solve x cubed equals 8? Well, among the real numbers, you know that there's only one real number whose cube is 8. 2 times 2 times 2 is 8. That's the only solution. That's the only real solution. By real, I mean real number solution. But what if I used complex numbers? What if I asked you to solve z cubed equals 8? What happens is I get 3 answers that are equally spaced about the circle of 360 degrees, just like these two square roots are equally spaced about a circle of 360 degrees by 180. Here, let's draw a picture. You understand that one of the answers to this equation, or this equation, whether you use real complex numbers, is 2. And this number can be written as 2 for the real number, or it can be written as 2 plus 0i. But now let's think of 2 other numbers that are equally spaced around the circle that both have a radius 2. What if I swung this? Remember, full circle is 360. So to cut that into 3 equal pieces would be angles of 120. So what if I swung that 120 degrees over here, but kept the radius of 2? So this would be 2 cis 120. Remember, that stands for 2 cosine 120 plus I sine 120 in parentheses times 2. That's the shorthand. What if I swung another 120 degrees? Well, I'd end up over here. Also 2 units long, but now this angle is 240. This would be 2 cis 240, which remember stands for 2 times, cosine 240 plus I times sine 240. I want you to see that these 3 complex numbers all make this equation true. These are called the 3 complex cube roots of 8. These are the 3 complex numbers that I could cube to get 8. Let me write them down, and I'll test them in the calculator. So the simplest one was 2 cis 0 degrees. That just radius 2 and cosine plus I sine of 0 degrees. Cosine of 0 degrees is 1, sine of 0 degrees is 0. So this is 2 times 1 plus 0i. The second one, 120 degrees later, was 2 cis 120. And the third one, 120 degrees later, was 2 cis 240. Let's type each of these in the calculator and cube it. I better get 8 each time. Okay, let's set the calculator down here. I'm going to keep it at ground level just so I can get some good lighting going on here. And let's type, now I cannot just type cis theta in the calculator. I have to say 2 times cosine of theta, cosine of 0, plus I times sine of 0. Even though I know that whole mess is just 2. Now let's cube it. Hang on a second. Let me go backwards. I got to make sure I have enough parentheses here, right? Okay, so now I've got matching parentheses there, matching parentheses there. Something tells me I have too many parentheses. That's a danger in writing this out. So I gotta get rid of that. And let's view this close up to make sure I got my parentheses in order. Let's get my numbers here on the side. Okay, cosine 0, sine 0, got it. I've got 1 too many parentheses right there. Okay, cosine 0, sine 0, then that parentheses belongs to that, and that parentheses belongs to the first. Now I've got the right number of parentheses. Let's cube it. Well, that's kind of anticlimactic because that was just the same as 2 cubed. Now let's cube one of these other guys. I'm just going to slip a 120 in place of that 0. So go back through my entries and let's insert 120 in place of that 0. Remember, I showed you the insertion key is right here. I don't got good lighting here. Let's try it that way. The insertion key is right here on the delete key. So I say second function, insert, put a 1, 2. Now I got 120 in there. Second function, insert, 2, not 1, 120. So this says 2 cis 120 cubed. And again, I get 8. Let's do it with 240 in place of 120. I can just write over 240 has 3 digits, 120 has 3 digits. I'll say 240, 240. The cube root is 8. So how can I turn this into a formula? What I did here. Visually, it's easy to start with, but how can I turn it into a formula? The z to the 1 over n has n roots. Always the nth root of the radius, but then I have cosine of theta over n plus I sine theta over n. But then I got to take the 360 divided by n. In this case, 360 divided by 3 is 120. And I got to add copies of that. Cosine theta over n plus 360 degrees over n times 1 plus I sine theta over n plus 360 degrees over n times 2 times 1. And this is very awkward to write because I one piece of 360 over n, then two pieces of 360 over n. I get n nth roots that go all the way around the circle till I stop with cosine theta over n plus 360 over n times n minus 1 plus I times the sine of theta over n plus 360 over n times n minus 1. I'll show you how he expresses this in the book, so you can look at that too. But you should not write down this formula. You should remember this picture. Let me try another problem. Let's pick another number, and not at random, but let's pick another number that I could calculate with relatively easily. Let's say that I want, let's pick a very mellow number like 1 plus I. And I want you to find the 5 fifth roots of this number. Let's draw the picture. And then take the fifth root of the radius and take equally spaced angles about 1/5 of this person's angle. So I need to convert this to trigonometric form, right? Now 1 plus I picked because it would have a very nice angle to work with. So here's Z equals 1 plus I. And if this triangle is 1 by 1, you know that this radius is root 2. So in trigonometric form, this would be root 2 cosine 45 plus I sine 45. And I like to write that in the shortened version, root 2 cis 45. Now, how can I find the fifth roots of this? This is 45 degrees here, right? So let me draw another picture. Let's make this a little bit enlarged. So I can draw several angles at once. If the theta in this Z is 45 degrees, then what does it mean to take the fifth root? I'll need theta over 5. 45 degrees divided by 5 is 9 degrees. And 9 degrees is kind of small. I mean, I don't even know if I can draw this nicely, but let's say that that angle right there represents 9 degrees. I won't tell you the length yet. But since I'm talking about the 5 fifth roots, what do I need now? I need 5 equally spaced angles that begin at 9 degrees. Now, what's 360 divided by 5? 72 degrees. 72 degrees is not a convenient angle for measuring, right? So, I mean, I know what 72 degrees looks like. 72 degrees might be relatively tall. 72 plus 9 is 81, which is getting pretty close to 90. But I don't want to draw like that. I want to draw 5 equally spaced angles that begin at 9. So when you think about equally spaced, do you think about a pentagon with 5 sides? How about, let me try to draw a pentagon. A pentagon is a figure that has 5 equal sides. I don't think I drew that perfectly, but here's a figure that has 5 equal sides. I want to space 5 angles out starting at 9, and they should have equal sides. So I'm going to do 81. I don't think I'm going to do this beautifully, but I'll do the best I can. Pictures are much nicer in the book. Then add 72 to 81, and you'd be at what? 153? Again, I'm just eyeballing this. And then 153 plus 72 would be 225. 225 is a famous angle, right? So I've got 9 degrees, 81 degrees, 153 degrees, 225 degrees. That's famous because it's 45 past 180. So that one should be easier to draw. I'll just make something that's exactly 45 degrees past 180. I got to do one more angle, split the difference here, come in about right there. I don't think I drew those perfectly equally spaced. But what's 72 plus 225? What do you guys say? 297? Let's write those down. 9 plus 72 is 81 degrees. 81 plus 72 is 153 degrees. 153 plus 72 is 225 degrees. And 225 plus 72 is 297 degrees. Now, these are 5 equally spaced angles, but what should their radius be? Because I want the 5th root of the square root of 2. What is the 5th root of the square root of 2? What's 2 to the 1/2 square root and then to the 1/5? By your powers of exponent rules from algebra, that's 2 to the 1/10. And I do not know what 2 to the 1/10 is. I'm going to have to ask a calculator. It's very close to 1. Let's just get a feeling for it here. 2 to the power 1/10. It's pretty close to 1. It's not super close, but 1.07, pretty small. So what are my 5 answers? This is the 10th root radius, 10th root radius all the way around. So I'll just write it once. Here's a picture of my 5 5th roots of 1 plus I. But now let me physically write them. The first one is the 10th root cis 9 degrees. I'm just going to repeat. And the 10th root of 2 cis 81 degrees. then the 10th root of 2, cis 153 degrees, then the 10th root of 2, cis 225 degrees, and the 10th root of 2, cis 297 degrees. These 5 numbers will all give me 1 plus I if I raise them to the 5th power. It's either the 1 to the 5th, it's either the 2 to the 5th, it's either the 3 to the 5th. I claim that they all give me the same result. Z sub 4 to the 5th and Z sub 5 to the 5th. I bet money that they're all equal to 1 plus I. Let's test it. But the problem with testing it is you know how awkward it is going to be to type in 2 to the 1/10 times the cosine of 9 degrees plus I sine of 9 degrees. Even with the replace feature that we used. Oh, sorry. Yeah. I want to look at there. Even with the replace feature we used, that was a bear to type that in. So is there a different way to type this in the calculator? And the calculator expresses complex numbers also. Go to mode. In this form called e to the I theta. E to the I theta is another abbreviation for cosine theta plus I sine theta. E to the I theta is another abbreviation for cis theta. So you could also write this number as 2 to the 1/10 e to the I times 9 degrees, or e to the 9 degrees I. Let me show you how to do that on the calculator. And the calculator screen here is so, maybe I should pull up the old calculator because these words are so small here, but let me see if I can type it for you. Let's get out of here. Quit. And type, can't show you the keyboard at the same time. 2 to the power 1/10 times E, it's right here on your keyboard. Down here, left of the 7, it belongs to this ln button, the natural log button. So e to the power, and then you say 9 degrees, but I'm talking about degrees, times I. Now, I got to be careful when I do this. Yeah. They want me to enter it in radian mode. I'm not prepared to enter that in radian mode. I don't want to use radians right now. It's easier to visualize this in degrees. I could write these in radians. You know, I could change 9 degrees to radians by multiplying by pi over 180. For 9, it wouldn't be such a pain. What would that be? 9 goes into 180 evenly 20 times. So this would be pi over 20. So I could express that like this instead of that 9 there. Let's say g pi divided by 20 times I. It still didn't like the way I typed it there. I got to be in radian mode, possibly, but I don't want to mess with this mode too much. I'll just do it the longer way. Let me first test that. See if that's easier. Now, for some reason, I'm not entering this nicely. So let's try entering one of these on the calculators just as is in cosine theta plus I sine theta mode. So what's 2 to the 1/10 times the cosine of 153 plus I times the sine of 153? And raise that to the 5th power. I want to show you that that's exactly 1 plus I. Now, by the rules, it's 1 plus I. This is 2 to the 5/10 times the cosine of 500, 750, and 15. That's 765 degrees plus I times the sine, 500, 250, 750, and 15 is 765 degrees. But the problem with that is I got to decode 765 degrees. Well, 2 full circles is 720, so that's not so bad. 720 less than 765 is 45. And what's the I sine of 45? I know what's 2 to the 5/10. That's 2 to the 1/2. So that's the square root of 2 times the cosine of 45, which is 1 over root 2, plus I times the sine of 45, which is also 1 over root 2. What's root 2 times 1 over root 2? 1. What's root 2 times 1 over root 2 in the imaginary slot? 1. That's 1 plus I, 1 plus 1I. But would the calculator recognize this if I typed it in like that? Let's type this in longhand on the calculator and get out of these goofy modes. So let's just go back to standard. Let me slide this paper up so we can see what we got. Let's go back to standard complex mode and type 2 to the 1/10 power times cosine of 153 degrees plus I times the sine of 153 degrees. In the 153, in the cis theta, and then end the whole complex number. Raise that to the 5th power. Now, a second ago, I went back to radians. I want to use degrees here. So let's make sure we're in degrees. Okay, we're in degrees. So let's say what happens if I raise that to the 5th power? Look at that, exactly 1 plus I. You can't even fit that whole thing on one line. But if you raise that to the 5th power, you get 1 plus I. What if we tried the 225? What if we tried the 297? Since that seems to be kind of like an odd number or a stranger number, the 225. Let's do 2 to the 1/10 cis 297. I still get 1 plus I. So if you want to take the 5th root of this complex number 1 plus I, you take the 5th root of the radius, that's the 2 to the 1/10, and you cut this angle by a factor of 5 to turn it into 9. And then the last step is you take 5 equally spaced angles around the origin by dividing 360 by 5 to mark every 72 degrees. This takes a deal of practice. So let me do one more just for practice sakes. And I want to keep numbering my pages as I go so you can refer to these later. Let's try one more. Then I might say a word about polar coordinates, but we can also save that for Wednesday. What if I wanted you to do the 4th root of 16? Now you first understand this as what number you multiply 4 times to get 16. And that's completely legitimate. If you multiply 2 4 times, you get 16. If you multiply minus 2 4 times, you get 16. But there are complex numbers I could multiply 4 times to get 16 also. So your first reaction is the 4th root of 16 is 2. But in the complex plane, there are a total of 4 answers to the 4th root of 16. Let's draw them. The first one will be 2 plus 0i. And if we cut that angle, now this is 2 times the cis of 0 degrees. 2 times the cosine of 0 degrees plus I times the sine of 0 degrees. That's 2 times 1 plus 0i. That's the 2 plus 0i. These are all different ways of writing 2 plus 0i. So if I take that angle 0 degrees and cut it in 4 pieces, I still have 0 degrees. Square root of 16, the 4th root of 16. But now I want 4 equally spaced angles around the circle. Now cutting 360 degrees into 4 pieces is easier than cutting 360 degrees into 5 pieces. 360 degrees cut into 4 pieces would be a 90. So that means my 4 answers are going to be equally spaced around the circle at 90 degrees. This is 2 cis 0 degrees. This is 2 cis 90 degrees. This is 2 cis 180 degrees. And this is 2 cis 270 degrees. And these are the 4 4th roots of 16. 2 cis 0, 2 cis 90, 2 cis 180, and 2 cis 270. Now the original number 16 was already had angle 0. Remember 16 is 16 times the cis of 0 degrees. So cutting that angle into 4 pieces started me off at 0. Let's write these 4 numbers down. 2 cis 0 degrees is just 2. But on the imaginary axis, 2 cis 90 is 2i. 2 cis 180 is on the other side of the real axis, that's minus 2. And 2 cis 270 is on the other side of 2i, that would be minus 2i. All 4 of these numbers have a fourth power of 16. 2 to the fourth is 16. Minus 2 to the fourth is 16. But 2i to the fourth is also 16. If you multiply 2i 4 times, you get 2 times 2 times 2 times 2, 2 to the fourth, and you get I to the fourth. I squared is minus 1, so I to the fourth is minus 1 times minus 1 is 1. So this is equal to 16. Minus 2i to the fourth is also equal to 16. You have to play with this several times before it seems natural. It doesn't automatically seem natural. But after you draw some pictures like this, you realize this is a quick way to calculate roots of complex numbers. Complex roots of complex numbers. Now, I want to say one more thing before we get going on Wednesday. So I'll quickly say something here about polar coordinates. We won't do any example. But it's possible you've never used polar coordinates before. So let me give you a quick introduction to polar coordinates. In the XY plane, you're used to describing coordinates or describing locations by saying, go this far left or right, and then go this far up or down. So if I want to describe to you the point 3 and minus 3, you understand the 3 stands for taking 3 steps on the x-axis. And the second coordinate, the y-coordinate, stands for taking minus 3 steps on the y-axis. That point right there is 3 and minus 3. These are called rectangular coordinates, or Cartesian coordinates sometimes, in honor of René Descartes, who had this idea of organizing points in the plane like this. But you could also describe that point in many different ways. Maybe instead of drive 3 miles east and 3 miles south, you could just tell people to fly straight to the point. Of course, if you want to tell them to fly straight to the point, like your carrier pigeon or your crow, you have to know how far away they have to go, and you have to know what angle they should take. But if I give you the x and y coordinates of a point, you can easily tell me what angle I'm using. Let's picture the same point, x comma y equals 3 and minus 3. But what radius would that be? If this is a 45, 45, 90 triangle, then that radius would just be leg times root 2. What angle would that be? Remember, you mark angles from the positive x-axis. So this is a 45-degree triangle, to be sure, but you're going down 45 degrees from where you started. So this would be angle of minus 45 degrees. So sometimes you see people describe this point not as xy equals 3 minus 3, but sometimes they describe the point in terms of its r and theta, and they write 3 root 2. I got to multiply that 3 times root 2, and minus 45 degrees. Let me write that neater underneath here. R is 3 root 2, and the theta is minus 45 degrees. When you write like this, using the r and theta, people call these polar coordinates, because you're kind of like circling the origin and going out a distance from the origin. Like you talk about North Pole, South Pole. Polar coordinates describe how far you turn and how far you go out. Because of the Pythagorean theorem, you can easily translate from one to the other. If you know the x and y, you can find the radius by the Pythagorean theorem. You can even find the theta, if it wasn't a famous theta, by taking the inverse tangent of y over x. If you know the r and the theta, you can find the x and y also by using a triangle. X over r is the cosine of theta, so x would have to be r cos theta and y would have to be r sine theta. You can translate from x and y to r and theta, or from r and theta to x and y. You can convert or translate from one system to another using formulas you already know. Now I gotta end it right here. And so we'll come back tomorrow and use these to draw pictures that might be hard to draw in Cartesian coordinates. You know, kind of beautifully symmetric pictures, but symmetry with respect to r and theta instead of symmetry with respect to x and y. And when I use these points to create graphs in the plane, when I use polar coordinates to create graphs in the plane, they're called polar graphs. So we didn't get to do an example like this today. I want to save these for Wednesday, but here's a quick description of polar coordinates. Practice doing those roots of complex numbers first, and we'll work on some polar coordinates and polar graphs together next time. Okay, I have to let you go there to be fair. So I'm gonna end this and get these notes and video posted, and you can finish up the homework problem you're submitting for tomorrow night, and I'll see you again on Wednesday. You guys have a nice day.